All right, we're up and rolling. Awesome. All right, let's take a look on page 425. We're going to take a look at slope fields. Okay, I think I told you guys on Friday last week, this is one of my favorite things that we're going to do all year because it's easy, and I think we're going to find it easy as well. You can plug in numbers into an equation, right?
What's an equation? Yes.
Yes, we can draw a line, right?
Yes.
Yes, then we're going to do great today. Okay, so a slope field is a visual, pictorial representation of all of the possible solutions that we can have to a derivative or differential equation. You know, when we work backwards, aka integrate, we have that plus c on the end if we don't have, or if we don't know the bounds. That plus c is just representing a constant. So depending on what that c value is, it changes where your graph is located. Obviously, adding 5 is going to put your graph somewhere different than if you were subtracting 7 on the end. So this slope field gives us a way to visualize where every antiderivative is located, no matter what the c value is. It's going to be a pictorial representation. And for those of you that have looked at wind graphs before, or topological graphs, remember how, I think if you're familiar with those, they show the elevation at certain points on the Earth. Maybe you're familiar with that. It gives us a way to kind of connect things together that have all the same height in terms of topological graphs, or in this case, all the same slope value. So we're going to take a look at how this might look like just in a simple case, and then we'll get into ones that are a little bit more complicated. Remember, f prime and dy over dx, they represent the same thing. Those both mean derivatives. So let's just start with this first one. How might we want to work backwards from dy over dx equals x plus 3? Can we integrate? Yes, we should. What do you want to do first? I see a y variable, I see an x variable.
Dx on the right.
We're going to separate, yep. dy equals x plus 3, and then dx. Variables are separate. If we work backwards, remember there's like a little understood 1 in front of that dy. So if we work backwards, we'll get y equals 1/2 x squared plus 3x, and then we need that plus c. Okay, we don't have a particular point in this case to help us figure out the c value, so we're just going to leave it like that. In the last section, we referred to this as the general solution, the general equation the original function kind of looked like. So we're going to go ahead and represent this, or write down, this is the general solution for the derivative equation dy over dx equals x plus 3, and it represents all of the quadratic functions, because notice how it's an x squared term. It's all of the quadratic functions that could have x plus 3 as a derivative. It doesn't matter if that c value is 100 or -2. If you took the derivative of that, you would get x plus 3. So what we're going to investigate today is how do we draw all of these different solutions. Because depending on that c value, we might get a different graph in a particular location. How on earth do we graph all of the solutions? Okay, all of these quadratic functions in this case. What does that look like graphically? So before we get into that, there are 4 different things that we must be able to do from this particular section. Okay, this is our goal, what we're going to be able to accomplish by the end of this section, most likely tomorrow. So we got to make sure we're able to do these 4 things. Okay, we're going to jot them down now, but then as we go through this section, we're going to reference them and make sure that we feel comfortable with these 4 key things. So the first thing we're going to try to do today is sketch a slope field when we know a differential equation. Differential just means derivative. We're definitely going to do that today. Once we have a slope field, we're going to draw, bless you, a particular solution, okay, an exact solution, and that must mean we have to know a point. Because remember in the last section when we were working backwards, the only way we were able to figure out a particular solution was if we were able to plug in an x and a y to get that c value. So the second thing, given a slope field, we can draw a particular solution curve through a point. We're definitely going to do these 2 things today. The next 2, most likely tomorrow. Okay, the last 2 kind of show up for multiple choice type questions on the AP exam, and they're not necessarily testing your ability to sketch a slope curve or draw a particular solution. These 2 most likely show up on free response type questions. That was the wind. The last 2 are more multiple choice. So if they're multiple choice, they should be kind of quick for us to kind of identify or label certain things that are going on. These are going to be matching games almost for us. So the first one is when we should be able to match a slope field to a differential equation, aka the derivative. But the other thing we could possibly match is match a slope field to a solution or solution, I guess, of solution of the differential equation. Remember, the solution is that antiderivative, that curve you get or function you get when you work backwards. So we're going to take a look at the first 2 today, the second 2 most likely tomorrow. All right, let's take a look at our first slope curve, or slope field, sorry. All right, so usually on a free response type question, they are going to give you a graph that kind of looks like this with all these different dots. And those dots are just representing the coordinates at particular points. So for instance, this dot right here is representing the exact point at 1, 1. What we're going to do is figure out what's the slope at that point, and we're going to go ahead and draw the slope at that particular point. We're going to sketch it. Okay, we're going to fill in all these different dots. Now, it might look a little overwhelming because there are a lot of dots, but you are going to see a pattern start to form after you do a few of them, so maybe we can use that pattern to our advantage. Okay, so let's just take a look at the directions I put up here for you to reference. Given the differential equation, notice how this is a derivative, okay, a differential equation, compute the slope for each point indicated in the grid, and then we're going to make a small mark that approximates the slope. Okay, so when I say small mark, I don't mean if we figure out a point that has a slope of 1, that is not a small mark. The small mark we want is only in relation to that point that we have. So you're not going to have big lines, you're just going to have like little tick marks as you go through. The other thing that we got to make sure that we're very, very good at and particular about is how we draw the slopes. So slopes of 0, 1, and -1 should be drawn exactly. Okay, they should be exact. Because if you think about drawing those types of slopes, we know a slope of 0 is flat. We should be able to draw that exactly. A slope of 1 is like a 45-degree angle. We should be able to draw that exactly. And then same with -1. That's another 45. The moment you start getting larger or smaller than those can be a little off. So in terms of AP testing and grading, they look at these first to make sure those are exact. And then all the other ones should be relatively close to what the slope should actually be. So if it's a slope of 2, obviously that should be drawn steeper than a slope of 1. I hope that makes sense. Okay, so these should be drawn exactly. So let's just go ahead and pick our first point. Does someone want to pick a point for us? It doesn't matter because we have a lot to go over anyway. 1, 1. Okay, so maybe we'll start here. Okay, so let's go ahead and take that point 1, 1, and we're going to plug it into our differential equation, aka our derivative. But if you take a look at this derivative we have, it's x minus 1. So we only really need to take the x coordinate from that point, which is 1, subtract 1 from it, which is going to give us an overall derivative, aka slope of 0. So this is one of our special ones. At this point that you picked, we need to draw a slope of 0, a small slope of 0. So we're going to just have a small horizontal line. You don't want to draw them long enough so they start to interfere with the other points on the graph. Okay, it should just be a small little mark. Let's pick another point. We have a lot more to go over. But the more we do, we might start to see a pattern.
2.
Say it again.
1, 2.
1, 2, okay. So we're going to take that ordered pair, plug it into our differential, aka derivative equation. We only have an x in it, so we only got to plug in the x coordinate. Looks like we get another slope of 0. So at that coordinate point, we have another flat slope. Maybe we can start to see a pattern just off of doing those first 2. Can we fill in any other points fairly quickly?
All the x equals 1s are 0.
Okay. All of these points right here that have an x value of 1, the moment you plug in 1 for x, you're always going to get 0, right? It doesn't matter what the y value is because we don't have a y value in that derivative equation. So let's just go ahead and fill in slopes of 0 for all those points. That was pretty quick. Let's pick another point.
2,
2, 1. All right. Plug in 2 for the x. Looks like we get 1. This is another special slope we should be able to draw exactly. So at the point 2, 1, it needs to be a perfect 45-degree angle, like you were connecting opposite corners in a square. So there's our slope of 1. Do you want to pick another point, or do you perhaps see another pattern we can fill in?
every point where x equals 2 is 1.
Okay, very similar to the last one. No matter what point you pick in this x equals 2 kind of column, I guess, you're always going to get 1 because there's no y value to change that slope. So for instance, if we pick 2 comma 2, that's still 2 minus 1, which would be 1. So all of these points need a slope of 1, perfect 45-degree angles. All right, let's perhaps pick the origin for our next one. We plug in 0 for x, we get negative 1. So at the origin, we need a perfect 45-degree angle, but this time it goes down. Probably following all of the other patterns we noticed. All of the other points that have an x value of 1 would have a slope of negative 1, or sorry, an x value of 0 would have a slope of negative 1 as well. Let's pick another point, maybe negative 1, 1. We plug in negative 1 for x, we get negative 2. All right, so this one's not one of the special ones we have to draw exactly. It should be relatively close to what the slope should be. So at that or at that point, we need a slope of negative 2, which is steeper than the negative 1s that we drew in previously. So this should be a little bit steeper than the 45-degree angles that we drew in the previous column. Very similarly, if we have another pattern, all of these would have slopes of negative 2 as well. If we pick another point, maybe negative 1, or sorry, negative 2 comma 1, we'll get negative 3 as a slope. So this should be even steeper yet than the negative 2s that we graphed before. Notice how they might get very steep very quickly, okay? But again, the 0, 1, and negative 1 are all of the exact ones. Everything else is just kind of in reference to those. Does that make sense? We completed our first slope field. What do you think? Not too bad? We're plugging in points and we're drawing lines. That's basically the whole idea. Let's try another one that's a little bit different. Given the differential equation, we're going to compute the slope. We're going to draw some more lines to develop our slope field. This one, though, does have an x and a y in it, so the y variable does change or affect the slope at hand. So it might be a little bit different to find a pattern. I'm not saying that there isn't a pattern, it's just probably not the same pattern we had in the last example. So what point do you want to try first for this one? Doesn't matter. We want to do the 1 and 1 again, like before. 1 minus 1 is 0. So at that point, we'll draw a flat slope. I see a lot of pencils moving. Do you guys want to try this one on your own? Give it a shot. Did anyone start to see a pattern after a while? It may not be the same pattern as the last one, but I think there's a pattern that we can discuss. What'd you find? Can you describe it? What do you think, Vinny? Sort of. Okay, so instead of being vertical, like the last example was, those all had the same slope. Now these are kind of on a diagonal, okay? So the first thing I noticed, you can plug in every single point if you want to get the slope exactly. But if you think about it, okay, you might not have to do that for every single one. For instance, when I first look at this, the first thing I notice is whenever x and y are exactly the same number, isn't that always going to have a slope of 0? Right? So 1, 1, slope of 0. 2, 2, slope of 0. 0, 0 is 0. -1, -1, 0. -2, -2, 0. So there's kind of that diagonal pattern that Vinny probably noticed. Okay? The next thing I noticed when I look at this is whenever x is 1 more than y, the slope would be 1. Okay, so 2, 1, slope of 1, and all those are going to have most likely the same pattern because it follows that diagonal pattern that Vinny noticed. On the flip side, if the y-coordinate is 1 more than the x, that would be a slope of -1. So 2, 3, -1. -1, -1, -1, -1. Do you start to see it taking shape? I'm not plugging in every single point. You could do that though. Okay. Let's see, if x is 2 more than the y, that's going to be a slope of 2. So those are even steeper yet. And then slope of 3 for the next one, and then 4. And then the rest of the graph is going to follow the same pattern, just negatively. So let's see, -2, -3, -4, and then -5. That's pretty steep. Did we get something that looked like that overall? Okay, so there might be patterns available. Use those to your advantage. Do you think we can draw a slope curve? Or sorry, a slope field? Pretty simple so far? Okay, that's the first thing that we need to be able to do. Okay, draw a slope field. We'll check that off of our list. The second thing, given a slope field, we're going to draw a solution curve through a point. So if we were to work backwards from this derivative equation, what would the solution curve look like? Let's go ahead and think about that. If the derivative is x minus 1, what do you think the solution curve would look like? Can you describe the shape of the graph? Quadratic. How'd you know? Good.
If you work backwards, it's going to be x squared.
It's going to be an x squared, okay? So you could think about it in your head. If you were to find that antiderivative, what would it look like? Maybe you can think about this. If the derivative is linear, like mx plus b, working backwards from that would be quadratic. Okay, you have those order of functions. So we'll say the derivative is linear. So the solution curves should be quadratic. So we're going to plot a particular point, and when we draw the curve, we're going to follow the slopes kind of as a guide, but we got to make sure that it looks quadratic in this case because we are able to determine that that's the shape. So let's go ahead and take a look at the point 1, -1. We would eventually use this to plug in x, plug in y, and figure out the c value like we did in the last section. But now we're going to draw the shape of this solution curve. So 1, -1 is right here. Let's go ahead and put a dot there. And we're going to trace the slopes to the left, trace the slopes to the right, and we're going to let the slopes be our guide. Maybe we'll try the right side first. So this point that we plotted, we know it has a slope of 0. So we're going to start off drawing it flat. But the further we go to the right, notice how the slope starts to become positive. So our graph should be increasing, like that. Notice how the slope of my curve that I drew is parallel to the slope in the slope field. Do you see how they are not touching? They're parallel. We're going to use the slopes as a guide. We're going to do the same thing but to the left-hand side. So we're going to start off flat because it was a slope of 0. But the further you travel to the left, your graph and the slope field should be parallel. So maybe it looks something like that. Does that graph look quadratic? Does it look like a parabola? I'd say so. All right, let's go ahead and try another one of these because I think that's the only example I had for that one. Can we flip back to the previous slope field that you guys did on your own on that page 426? I want to go over something here. Let's plot a point. We'll say at -1, 2. So that's right here. If you draw the slopes to the left, they're pretty steep. But as you draw the slopes to the right, keeping them parallel, notice how you'll eventually become flat because we had those slopes of 0. And then we'll go off to the right. So that's what the solution curve, aka the antiderivative, looks like at the point -1, 2. But what if I were to pick a different point? What if we tried 1, -1? Somewhere right here. If you trace the slopes to the right, and you trace the slopes to the left, it's a different curve, isn't it? It looks different. Okay? So the point matters. Depending on where that point's located, your solution curve may look different than a different point would generate. It's still the same solution graph, okay? It's still the same slope field antiderivative graph, but it depends where the point is located for you to give you that shape. Yeah?
Whenever we put a point down, what slopes are we tracing?
You're not necessarily tracing over the slopes.
Well, yeah, but what slopes are we replicating?
The ones that are closest to that. So if I were to start here and trace to the right, I should be replicating something relatively close to those. Okay? The further you go to the right, you should be replicating something close to what's around your pen or your pencil. Okay? So you're not necessarily tracing over the lines you drew. Okay? It's just you're replicating the slopes around them. Okay? So the point matters. Okay, that's important. Make sure that you plot the correct point and then trace it appropriately. Can we do that? That's our second thing. Can we plot a point and follow slopes? All right, let's try the third one, kind of our matching game. For this one, you're going to go ahead and have to reference pages 249 and 248. Okay, we have the graphs on page 428 and 429. So the graphs on 428 are those slope fields that we practiced generating before. These were just done on a calculator. And then what we're going to try to do is match these differential equations to the slope fields. Okay, so if you were to pick a point and plug it into these different differential equations, it would generate the slope field that's given. All right, so let's see if we can perhaps tackle some of these. Now, it's not necessarily saying that the slope field looks like these. Okay, the slope field represents the slope of these provided graphs. So let's think about this. If we were to work backwards from sine, okay, let's say we separated the variables as such, and we worked backwards. We'd get y equals, what's the antiderivative of sine? Say it again?
Cosine x.
Close. Negative cosine x. Okay, and then we have that plus c. All right. Let's go ahead and try to work backwards from all of these. We might not get to the actual matching part today, but we'll see if we can work backwards. What about the next one? If we work backwards from 2x plus 4, be x squared plus 4x, and then plus c. Let's see, if we work backwards from the next one, we get e to the x. Backwards from 2, we get 2x. Backwards from the next one, 1/4, x to the 4th, minus 3/2, x squared. Backwards from cosine would be sine. Let's see, backwards from the next one, 4x minus x squared. Next one would be 1/2 x squared. We got 1/3 x cubed. What about backwards from 1 over x? Yeah?
Natural log of negative x?
The negative would just be out front.
Okay, that's what I thought.
That's okay. Natural log. Good. Okay. So, what we're going to do tomorrow, because the bell's going to ring in a little bit, now that we know what the antiderivatives are, aka the solution curves, the general solutions to these differential equations, we're going to play a little matching game. Okay, which slope fields look like these solution curves that we developed? Okay, those antiderivatives. I forgot my plus c's on the end.